Hello, and welcome to your final lecture in Unit 3 on equilibrium. In this last lesson, we are going to be looking at how to do a little bit more complicated calculations that involve equilibrium, constants and equilibrium concentrations and initial concentrations. Before we get into the more complicated calculations, I want to review for a second the types of calculations we have done already. Because in this unit, we've done a lot of conceptual stuff, right? But we have done a couple pretty simple calculations. And those involve either calculating the value of K given equilibrium concentrations, or we could be given K and all but one of the equilibrium concentrations, and we calculate that missing one. So let's review those really quickly. So the first is, if we have all of the equilibrium concentrations, we can just simply calculate the value of K. So for this question, we are given the reaction nitrogen plus hydrogen in equilibrium with ammonia. And it gives us the equilibrium concentrations and asks us to find the value of K. So the first thing that I have to do is I have to write my K expression. So products over reactants raised to their coefficients. And now I'm simply just going to plug in my equilibrium concentrations that I was given in the problem. So 0.412 squared over 1.35 cubed, 1.15. And when I simply do that math, I get 0.06. Super simple, plug and chug. We've been doing this since the beginning of this unit. Another type of calculation that we've probably already done is we might be given K and then a couple of the equilibrium concentrations, and we have to find the missing one. So in this question, it's the same reaction as on the prior slide. So we've got nitrogen plus hydrogen in equilibrium with ammonia. But this time we are told that K is equal to 0.06. All right, so instead of solving for that, we are told that K is equal to 0.06. So now I'm going to write my K expression, but I know the value of K. And then I'm going to plug in what I know. I don't know the ammonia's concentration. That's what I'm solving for. But I know that nitrogen is 4.26 and hydrogen is 2.09. So then when I do that math, I get that the concentration of NH3 squared is equal to 2.33. So I just cubed this and multiplied by this and then multiplied that by 0.06. So then when I take the square root, I get that the concentration of NH3 is equal to 1.53. So again, nothing tricky at this point. We've already done all of this. So now we're going to take it up a notch, and we're going to do some that are a little bit more complicated. When we get to these more complicated equilibrium calculations, we're going to use something called the ICE method. If you look up videos, you might also see it called the Rice method. So the R, if you do see it called the Rice method, just stands for the reaction. But I've always called it the ICE method. I stands for initial, C stands for change, and E stands for at equilibrium. So if you remember back to the POGIL that we did on the reaction quotients, the first model was written with the charts in this form. So we're given the initial concentrations or initial pressures, then we have what's the change, and then we have what are they at equilibrium. So when we are looking at how the concentrations change from initial to equilibrium, those are going to be related by their stoichiometric coefficients. And I'll show you what I mean by that. So I have it written on the slide, but I'm going to rewrite it in the form of an ice chart. So I have my reaction, 2NH3, in equilibrium with N2NH2. All right, so initial change equilibrium. Now, for this example, I'm not told my initial, but I'm told that the concentration of N2 increases by 0.11. So then I know that my change here is 0.11. Okay, so then if I am adding N2, which is a product, then I'm also going to be adding H2. And I'm going to be adding 3 times the amount that I added of N2 because of the coefficient 1 and 3. Now, if I'm creating product, then I'm losing reactant. And so over here, it's going to be a minus sign, and then it's going to be 2 times the change. So all I do for the change row is I use a plus for the side that we're shifting to, or most of the time the products, and then I use a minus for the side we're shifting away from, typically the reactants, and then I use the coefficients to know by how much that change is going to be. In a lot of problems, we're not going to know the exact change. So instead, we are going to use X as a variable to stand in for that amount. So in this case, then, instead of having that 0.11, we just have in our change row plus X plus 3X minus 2X, okay? So we always use a minus when we're shifting away, which is usually the reactants. Sometimes we may keep a reaction written and then go the reverse direction, and so then the minus would be in what's technically written as the products. However, you can always rewrite a reversible reaction, and so then always it would be minus in the reactants, and then a plus for shifting toward, which is usually our products. So let's do some examples of predicting the change. So I have no reason to think that this is not going from reactants to products. So for all of these, I'm going to do minus in my reactants and plus in my products. So for the first one, I have minus X for C2H2. So then Br2 would be minus 2X, and then the product would be plus X for my coefficients of 1, 2, and 1. For this one, I have plus X for I3 minus. So in the reactants, I have minus X and minus X. All of them had a coefficient of 1. Here, I have minus X in the reactant. So then for 5O2, it would be minus 5X. And in my products, it's going to be plus 3X and plus 4X. So for that row of C, in our ice chart, we just use a minus for the reactants, a plus for the products, and then we use the coefficients. Okay, so for these more complicated calculations, we kind of have 2 types. We could have to calculate K given some initial concentrations and then at least one equilibrium concentration. That's the easier of the 2. Or we could have to calculate all of the equilibrium concentrations given both initial concentrations and the K value. So we're going to go through examples of both and how to do them. So for this first one, we are calculating K given a combination of initial concentrations and an equilibrium concentration. So we're given this reaction, and we are told that the concentrations of the reactants I2 and I minus are both 1 times 10 to the negative 3. And then we are told that the equilibrium concentration of I2 is 6.6 times 10 to the negative 4. Now I'm asked to find what's the equilibrium concentration, or excuse me, what is the equilibrium constant? So I'm going to make an ice chart and I'm going to plug in what I know. So I was given this reaction, I was given these initial concentrations, and then I was given the an equilibrium concentration of I2. Now I have nothing in this question tells me that I have any I3. So if I am not told a concentration of product, I'm going to assume 0. So then, of course, this reaction is going to proceed to the right from reactants to products because I don't have any products. So now I can fill in my change column, minus x plus x. So then I can combine the I and C to get to the equilibrium. I already know that I2's equilibrium concentration is 6.61 times 10 to the negative 4. I already filled that in. But for I minus, I'm going to take then 1.0 times 10 to the negative 3 minus x, and then 0 plus x, which of course just equals x. So now that I have filled in everything I know with my ice chart, both actual values and expressions, then I can because of the fact that I was given one of my equilibrium expressions, I can combine I and C and set it equal to E and make this into an actual mathematical expression. 1 times 10 to the negative 3 minus x equals 6.61 times 10 to the negative 4. So then what I'm going to do is I'm going to solve for x. So when I solve, I get x equals 3.39 times 10 to the negative 4. So I'm trying to solve for k, right? My whole point of this question was to calculate the k value. So in order to calculate k, I have to have equilibrium concentrations because that's what k is. K is at equilibrium. So my equilibrium expression for this reaction, products over reactants raised to their coefficients, which in this case all the coefficients were 1. So now I'm going to take this x and I'm going to plug it in anywhere that there's an x in my equilibrium row. So then I get that I minus is 6.61 times 10 to the negative 4, and I3 minus is 3.39 times 10 to the negative 4. So then I plug all of those values into the k expression, and I get my new value, or not my new value, but I can calculate the value of k. So let's do another one from scratch. So a 0.72 mole sample of PCl5 is put into a 1 liter vessel and heated. At equilibrium, the vessel contains 0.4 moles of PCl3 and 0.4 moles of Cl2. Calculate the value of the equilibrium constant. So the whole point of this question is to calculate K. All right, so first of all, I need to write a balanced equation. So PCl5 decomposing Cl3 plus Cl2. So that's already balanced, so I don't need any coefficients. So then I'm going to set up my ice chart. I am told that initially I have 0.72 moles of PCl5. It's in 1 liter, so 0.72 divided by 1 is 0.72 molar. Nothing in my question tells me that I have any product, so those are 0. Because I have no product, then I am, of course, going to go to the right. So I'm going to minus my reactant, minus x, plus x, plus x. I'm also told then that at equilibrium, I have 0.4 moles PCl3 and 0.4 moles of Cl2. So I don't know how much I have of PCl5, but I do know that I have 0.4 molar and 0.4 molar. So now I can set up my K expression. Whoops. All right, and now I'm going to plug in my equilibrium concentrations. But before I do that, I got to solve for this x value right here. So I have 0 plus x equals 0.4. So of course, x equals 0.4. So then 0.72 minus 0.4 is 0.32. So now I know all of my equilibrium concentrations and I can plug them in. 0.4, 0.4 divided by 0.32. And when I do that math, I get 0.5. So I calculated my equilibrium constant starting with an initial concentration, and then I was given some equilibrium concentrations. So now, the next type of calculation, we're going to be given initial concentrations, and we're going to be given the K value. And we have to solve for the equilibrium concentrations. So for people who like to have a step-by-step process, I have those steps written out here. And in the next couple of slides, I'm going to go through them, go through how to work this problem following these steps. Now, when you actually work these problems on your own, you don't need to write out step 1, step 2, This is just for people who like in their learning process to have actual steps. So we're going to always start with a balanced chemical equation if we're not given one. Then we have to figure out which way our reaction is going to proceed. Is it going to go right or is it going to go left? This is really obvious in problems like we've done before because we didn't have any product. So we, of course, are going to go to the right. But if we do start with some concentration of both reactants and products, we're going to have to calculate Q to see if we're going to go right or left. Once we've established that, we can fill in our initial concentrations of our ice chart. We can fill in the C row, and then we can fill in the E using the expression of combining I with C. Then we plug in those E expressions to the equilibrium expression, set it equal to K, and solve for X. So what does this even look like? All right, so here's a question. Under certain conditions, the equilibrium constant for the decomposition of PCl5 into PCl3 and Cl2 is 0.0211. So immediately we are given the K value. What are the equilibrium concentrations of PCl5, PCl3, and Cl2 if the initial concentration of PCl5 was 1? So you can see how this is a type of problem where we are given K and we are given an initial concentration, and we have to solve for the equilibrium concentrations. So step 1, I write my balanced equation. Step 2, I got to figure out which way does my reaction proceed. Well, I'm given only initial concentrations of a reactant. So the only option is to proceed forward or to the right towards the products. So then now I'm going to fill in my ice chart. So I have my reaction here. Then I know I have 1 molar initial concentration of PCl5. I have no PCl3 or Cl2. I know it's going to the right, so this is going to be minus X, and plus X. None of those had coefficients because all of these coefficients are 1. Okay, so now I can combine the rows I and C and set them equal to E. So 1 minus X, 0 plus X, and 0 plus X. So now that I have my ice chart filled out, I'm going to take my equilibrium concentration row and I'm going to plug it in to the equilibrium expression. So of course 0 plus X simplifies to X. Okay, so that's why I have just X's here. So from the previous slide where we saw the problem, we know that K is equal to 0.0211. So I'm going to do 0.0211 equals X times x divided by 1 minus x. Okay? Guys, we are bringing back some serious algebra. All right? So we need to simplify this. So I got x times x is, of course, x squared. And then I'm going to take 1 minus x, and I'm going to multiply it on the other side. Then you got to remember, you have to distribute. So 0.0211 times 1 is 0.0211 minus 0.0211 times x equals x squared. Now, I like positive numbers, so I'm always going to put my x expressions where my first x squared is going to be positive. You can absolutely do it to the other way, doesn't matter. If you'll notice, I'm setting this up like a quadratic. X squared plus 0.0211x minus 0.0211 equals 0. So all I did was I moved this over here and I moved this over here. If I have a quadratic expression, that means I have to use the quadratic formula. All right, so refresh. Opposite of b plus or minus square root of b squared minus 4ac all divided by 2a, all divided by 2a. All right, so I still remember that from math class in like 9th grade. I don't know, whenever I took algebra 2. Okay, so I'm going to plug in all of these values. So I have negative 0.0211 plus or minus the square root of 0.0211 plus 4 times 1 times negative 0.0211 all divided by 2 times 1. When you do that in your calculator, you are going to get, always for quadratic formulas, 2 values of x. You can graph this if that's how you solve for x when you do quadratics, or you can plug it into the quadratic formula. It does not matter. You're going to get 2 answers. Most of the time, one of your answers is going to be negative. We can't have a negative concentration. So we pick the positive x. Every now and again, you won't have a negative x, but you will have an x that's larger than the initial concentration, which would leave you with a negative concentration at equilibrium, and that's also not possible, okay? So solving from the quadratic, we get that x equals 0.135. So now that I know that x is equal to 0.135, I'm going to plug it in everywhere there's an x, which gives me that the equilibrium concentration of PCl5 is 0.87, and then PCl3 is 0.135, and Cl2 is 0.135. Then I can always do a common sense check, because I can plug these equilibrium values in to my equilibrium expression, and I can check to make sure that I get the Kc we were given. Okay? So, for those of you who are about to have a heart attack because we just pulled out the quadratic formula, we're going to do a few more practice problems that do involve the quadratic formula. Then I'm going to let you in on a little secret that will allow you to avoid using the quadratic formula. You can avoid it like the plague. But I'm still going to do some more examples with you with the quadratic formula first. Okay, so I know you're going to miss seeing my beautiful face, but so that I can write better, took the camera off so I can flip the tablet. Anyways, okay, so we're given this reaction, and we're told that the K value is 0.078 and gives me the initial concentration of SO2Cl2 and asks me for all 3 equilibrium concentrations. So the first thing I'm going to do is I'm going to set up my ice chart. I already have my balanced chemical equation, so I'm just going to rewrite it. I don't have to balance or anything. And then my initial concentrations, nothing to tell me that there's any product. And because there's no product and only reactant, we are, of course, going to shift right. So then my change column is minus x, and plus x. So now I'm going to combine my I and C row to equal my E row. 0 plus x is just x. 0 plus x is just x. Okay, so now my general expression for K but then I know that K is 0.078, and I'm going to plug in this row. So I have x times x over 0.250 minus x. So now I have to simplify this. So when I do, I'm going to have 0.078 times 0.250, which is 0.0195. Then I also have 0.078 times x, and then that equals x squared. So then putting them all on the same side, I have x squared plus 0.078x minus 0.0195 equals 0. So I set that up in quadratic form. So now I'm going to plug that into my quadratic formula, or graph it if you prefer. When I solve, I get x equals 0.106 or negative 0.184. Well, we know it cannot be negative, so my x value is 0.106. So then my concentration of SO2 at equilibrium is 0.106. Whoops. And then 0.25 minus 0.106 equals 0.14. So my answer to this question is 0.14, 0.106, and 0.106. On a quiz or test, if you write your ice chart and you put your answers kind of under the E row like I did here, that would be perfectly acceptable. Or you can always write them off to the side if you prefer. So at equilibrium. So you could write this either way. Okay, so let's do another one that involves the quadratic formula. So I'm given my reaction, and I am going to make my ice chart. A 1 liter flask is filled with 1 mole of H2 and 2 moles of I2. Well, easy to find my concentration because 1 divided by 1 is obviously 1, and 2 divided by 1 is 2. So it's 1 molar and 2 molar. So 1 molar is my initial concentrations, and I don't have any HI. So because I have no product, I'm of course shifting right. So this is going to be minus x, minus x. This is plus 2x because of that coefficient of 2. So now I know that 1 minus x, 2 minus x, 0 plus 2x just gives me 2x. So now my K expression, I always write the general expression first. so I don't make accidental mistakes forgetting my superscripts. So now I know that Kc is equal to 50.5 because I'm given that in my equation. So then I have 2x squared over 1 minus x times 2 minus x. Okay, so this one's a little bit more complicated to simplify. So I have 50.5. Now I'm going to multiply it by this FOILed. So 1 times 2, 1 times minus x times 2, minus x minus x. So that is 2 minus 3x plus x squared equals 4x squared. So I get 101 minus 151.5x plus 50.5x squared equals 4x squared. Simplifying that to get it all on one side in a quadratic form. Whew. All right. Again, for those of you who are like, oh my goodness, this is absolutely ridiculous, I'm about to show you a way that we can avoid doing this. So I'm going to plug this into the quadratic, or you could graph it. I'm going to get two possible x values, 0.935 and 0.2323. Now in this case, neither of these are negative. However, if you look at where you're going to be plugging in x, 1 minus 2.323 is going to give me a negative number. That is not possible. So my x is equal to 0.935. So 1 minus 0.935, 2 minus 0.935, and 2 times 0.935. So then my equilibrium concentrations are 0.065, 1.065, and 1.87. Okay, so that right there is kind of as hard as it gets. So let's ease up a little bit. So there is a way that we can ignore the quadratic formula. It's super time consuming, and the College Board is not actually trying to test your ability to do the quadratic formula. So there is always going to be a way to ignore x. It's either going to be because you're going to get like x squared divided by x squared, and we can cancel that out, and so you don't have a quadratic, or by ignoring x. We can ignore x if the value of K is significantly smaller than the initial concentrations. And I'll show you what that looks like. The reason we can ignore x when this is the case is because the final concentration will be less than 5% of the initial concentration. So if you're someone who's like, oh, it makes me feel really weird to ignore this x, I feel like I'm doing something wrong, you can always check to ensure that you were right in ignoring x. When you get your final answers for your equilibrium concentration and you divide them by your initial, you should get less than 5%. So let's do a couple examples where we can ignore x. And for any quiz or test, you will be able to ignore x. Let me repeat, you can always ignore x. All right? I teach the quadratic formula way because that is the true answer. But because we are not testing your ability to do the quadratic formula, we can do these shortcuts. Okay, so calculate the equilibrium concentrations of both species in 1 liters of a solution prepared from 0.129 moles of N2O4 with chloroform as the solvent. That's kind of terrifying. Chloroform, not good. Okay, so we have our balanced equation. And I am told that my initial concentration is 0.129 moles per 1 liter, so 0.129 molar. I don't have any NO2, which means this has to shift right, so minus x plus 2x because of that coefficient of 2. So then my equilibrium values are 0.129 minus x, and then 0 plus 2x, which is just 2x. So now I'm going to write my K expression. N2O4. And I get, or excuse me, not I get, I know that K is 1.07 times 10 to the negative 5. Okay. Notice here, 1.07 times 10 to the negative 5. That is an extremely small number. That is way, 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 way smaller than my initial concentration. So what that means this is the X that I can ignore. All right, because whatever X ends up being is going to be so much smaller than 0.129 that with rounding, my equilibrium concentration is going to be extremely, extremely close to 0.129. So I can ignore that X. Now, when I'm starting with 0, I absolutely cannot ignore an X there, okay? So the X that gets ignored is the change in X from the initial concentration. So now, because of being able to ignore X, when I simplify this, I have 4x squared is equal to 1.07 times 10 to the negative 5 times 0.129. 4x squared equals 1.38 times 10 to the negative 6. So when I divide that by 4 and take the square root, I get 5.87 times 10 to the negative 4. So that is my value of X. So then the question asked me for my equilibrium concentrations. So when I do 0.129 minus 5.87 times 10 to the negative 4, I get 0.128. So that's why ignoring that X was allowed, because the change is so insignificant. So then my concentration of NO2 is 0.00117. Now, again, if you're someone who is like, I don't know if I was allowed to ignore X if I did that wrong, if I take my final concentration and divide it by my initial concentration in order to find the percent, I get that it is like 0.45% of it. And so as long as it's less than 5%, we are good to ignore X. All right, y'all, so let's do another one where we do get to ignore X. And I can see that initially I'm going to be able to ignore X because of this really small K value. So when I tell you that on a test you're not going to have to do the quadratic formula, I'm telling you that you're going to be given questions where the K value is so small that you get to ignore X. All right, so I'm going to set up my ice chart. I'm given my initial pressure of 0.824. I don't have any product. Because I have only reactant, I know I'm going to shift to the right. So minus 2x plus 2x plus x, 0.824 minus 2x, 2x, and x. Okay, so I'm going to write my Kp expression. So pressure of H2 squared times the pressure of S2 divided by pressure of H2S squared. So now I know that my Kp value is 2.2 times 10 to the negative 6 equals 2x squared times x over, now because this K value is so small, I can ignore this change in x, okay? Even though it's 2x, x is going to be so small that the change is insignificant. So I get to ignore that x, okay? So now I'm going to get 1.494 times 10 to the negative 6 equals 4x cubed. So then x cubed equals 3.73 times 10 to the negative 7. The way that you get rid of cube is to take the cube root or to multiply by 1/3. So then x equals 7.2 times 10 to the negative 3 atmospheres. So now I take that x value and I plug it back into my equilibrium. So 0.824 minus 2 times 7.2 times 10 to the negative 3, 2 times 7.2 times 10 to the negative 3, and my concentrations at, or excuse me, not concentrations, my partial pressures are 0.810 atmospheres. H2 is 0.014 atmospheres, and S2 is just the 7.2 times 10 to the negative 3 atmospheres. So I just plugged in this x value up here into my equilibrium row.